I'm not 100% sure how to pronounce it, but Delaunay Triangulation is an algorithm for creating a triangle mesh from a set of unconnected points. You can use it as a prerequisite for a bunch of cool animations, including cloth simulations, and today we're going to be learning how to do this in Geometry Nodes using Blender 4.2. So let's get into the overview. First, we'll import a curve. We'll create a mesh from that curve, and we'll create a resampled version that's converted to points. Then we'll combine these two geometries and distribute a bunch of randomized points on the faces of the mesh. We'll then perform a simulation only on the blue points to distribute them more evenly across the surface. We'll create a starting triangle that encompasses all of our points and iteratively refine it to get our final triangulation. The algorithm works by iterating through all of the points and checking to see if any of the triangle's circumcircles include that point. If they do, we'll delete those triangles and then collapse them on that point so that they no longer contain it. If we do this over and over again while cycling through all of the different points, we eventually arrive at our final destination. Then we just have to delete any triangles which don't intersect with the original mesh, and we are good to go. And now it is node time. Starting with an empty scene, Shift A to add a cube, and then add a new Geometry Nodes window, and click New to create a new Geometry Nodes network. Next, we'll need to pull in an object from our scene, which doesn't exist yet, but if we just add that object info node, we can then pull in our SVG, which we got from blender.org, and we're going to be using this Blender logo SVG. So if you just click and drag into the viewport, just import SVG as grease pencil, and then let's just hide the cube for now. And we'll want to convert the grease pencil after you open this menu. Convert grease pencil to a curve. Let's just do a polygon curve. And then we're just going to want to delete everything that we don't need. So first let's select this, Control L. After left clicking, just like the rest, I'll delete the points. This is the old one. So this is our curve, this is our grease pencil. We can just delete the grease pencil. We can just keep these curves. Go back into edit mode, select this, Control L, and actually we can shift, click, and drag a box to select all of that. Control L to make sure we have everything connected, selected. X to delete. We can move this over. And what else do we not need? We don't need this outer line. So select there, Control L, X, delete. And now we have the curve that we want to work with. Let's just put that in the center. So we can now show our cube again. We can actually hide the curves, and let's hide them in both the viewport and the render. And let's jump out of edit mode using tab, come back to our Geometry Nodes network, and then pull in the curves here. Get rid of that group input. And so now you can see our curves that are now in our Geometry Nodes network. Our first step will be to resample these curves, or this curve. So let's resample that. Let's set it to length, and then let's do something low, like 0.02. And then we'll want to fill the curve. So add a mesh to it. We can just set that to triangles. Oh, and we have an issue. This is 2D, and you can see that it's going along the z-axis, and that won't work for fill curve. So what we need to do is actually go back into our curves geometry. That's how we're going to do this. Alt to deselect, and you can press A to select everything if it's not already selected, and then R to rotate, X to rotate around the x-axis, and then we'll hit 90, and then negative to flip that direction. And now you can see that it's filling the curve correctly. And actually that's not at the origin, so if we want to snap to the origin, we can press period to open this pie menu, and then we're going to use the 3D cursor as the origin point for transformations, and then S to scale, Z to scale along the Z-axis, and then 0 to just zero that out. Tab out of edit mode, we can hide this again, and now we can see the meshing is working correctly. So now what we need to do is add some points on the faces of this mesh, and then relax them so that they are distributed in a more even way. So first we can use a distribute points on faces node. And let's set that density to something pretty high, like 4096, and we're getting an error here, and that's because I have the wrong input. So if you put the output of the fill curve, which is the mesh, then you can distribute points on faces. Let's set the point radius be something smaller so we can actually see. 0.002 will work for S. And then we're also going to want to, before we do the simulation, we're going to want to take our resample curve and then convert that curve to points, because we want to use that in our relaxation simulation as well. And these points, which also set the point radius. Here, let's do a little bit bigger. Ooh, that feels very wrong. Everything about that feels very wrong. This is because we have the curve to point set to count, and so we just get 10. But what we really want is evaluated, because we already resampled the curve. So those are our points, and what we want, if I join these two pieces of geometry, is we want these points to stay the same on the outside and these points in the middle to move and become more evenly distributed. So what we're going to do is set up an attribute called pinned. So store named attribute, set to Boolean because it's just true or false. We'll name it pinned. And so we're only going to set this for the outside points and just set that to true. And by default, it'll be set to false for these ones. For our simulation, we'll start off with a simulation zone just to see how this works. But later on, we'll just switch that to a repeat zone and set our iterations to an amount that we like. So let's just put this geometry into our simulation loop. Keep hitting skip on accident. And then we're going to want a set position node, because essentially what we're going to do is every frame we're going to look for the closest point from all the points for any of the points that we want to actually move, so excluding these boundary points. And then we're going to move it away from its nearest other point. And we're just going to do that many, many times so they kind of have a repulsive force against each other, and that'll converge onto a nicely distributed set of points. So we're going to set position, and we only want to move the non-pinned points, so those that have the pinned attribute set to false. So we'll do a named attribute, which is going to be a Boolean called pinned, and then we'll do a Boolean math set to not. And so if it's not that, then we will actually move these. So the way that will work is we're going to get the index of nearest. So this will get the index of the point in the geometry that is nearest to the current point being evaluated in the set position node. And then we will use an evaluate at index node. Shout out to Arendelle for messaging me and saying, hey man, you've been using the sample at index, or sample index, which is like for this purpose, because I could use the sample index and I would just have to make sure that I input the geometry, but I'm using the same geometry, so I can just use the evaluate index. So thanks to Arendelle for giving me that pointer. Makes the node network a bit simpler. And so you pop that into the index. We want it to be position. This by default I think is this. You could always put that in there to make sure that yeah, you're getting the nearest index closest to that position. I don't know, it works. And so what we'll do is we'll then subtract. So we're trying to get the vector that points from the nearest, the point that is denoted by the index that comes out of the index of nearest node to the current point. And so we just have to do this position and then subtract this position. And then we're just going to scale that down because we don't want these points to move too much because they won't converge as well if you don't do this. And then we'll just pop that into this offset. So then if you run the simulation, you can kind of see them moving and getting nicely distributed, but you have these issues here where these points, in fact, you know, I don't even need to do this whole pin thing. I think at one point when I was testing this out, oh no, it works. Yeah, no, it works because they're also getting repulsed by these points. Never mind. Anyway, so these floaters that come out, we're going to fix that by adding one more set position node here. And what we're going to do is we're going to take that mesh that we created here, and then we're going to sample the nearest surface point to the given point, and we're just going to set that as the new position so that those points never actually leave the bounds of the mesh. So if we do sample nearest surface, and we're going to sample this mesh, so we can just grab that, and we're going to do a vector as the type of attribute that we're sampling because we're going to sample the position. Again, I'm going to redundantly plug that in there because I just like to do that for clarity. And then you just set the position there, but also make sure to also only do this for the unpinned points, because the pinned points, we don't want them to move at all. And then if I unclick that viewer, I could just delete that. Now when we run our simulation, nothing works because I did it wrong. What did I do wrong? Sample position, vector. This is the mesh. Fill curve. What have I done? Oh, I plugged this into offset and it should be in position. So now you don't get those floaters, everything distributes really nicely, and let's see, like it gets pretty good on like 44 frames. 80 is a good number of iterations, and so what we'll do then is we'll replace that simulation zone with a repeat zone. We'll set the iterations to 80. Well, let's keep them at 1 for now until we set everything up. So just pop this there and pop this here. And this is the same input. Then you'll want this to go to here instead of this one. And then this to go to there instead, and then that to go here. Delete that simulation zone because we don't need it anymore. And then you can see you get the same simulation depending on the number of iterations you set. So let's set that to 80. And we are good. Moving on to the actual Delaunay triangulation algorithm. First, we're going to add in a bake node. And this is just to bake all the operations that happen in this repeat zone, so we don't have to recalculate those. We'll just bake at frame 1. And then what we're going to want to do is first we need to create a triangle that contains all of the points. The way that we're going to do that is we're going to use an attribute statistic node, and we're going to get position, and we're going to get the maximum length. So let's do vector math, and let's do length, and put that there. And then we'll create a curved circle. The resolution is just going to be 3, so that's going to be a triangle. And let's get the max and add the radius, and I think that's going to have to be multiplied by 2. or 2-ish. Yeah. So let's multiply by 2, 2.1 just to be safe, because we just need it to contain all the points. So we'll just leave it at that. We need that curve to be filled and converted to a mesh, so we'll just add a fill curve node. And now we've got our starting triangle. And then we're going to do the whole algorithm within a simulation zone. And the simulation iteration will, or the frame, will determine which point we're checking against. And then every frame, we're going to check all the faces. We're just going to use, we're not going to use like a for loop or a repeat zone or anything like that. What we're going to do is we're just going to use attributes of faces to check to see if any of them don't meet the conditions necessary for a Delaunay triangulation, which is the circumcircle of the triangle. It cannot contain any of the points within the points that we're worrying about. And the circumcircle is just like the circle that touches all 3 points of the triangle. And so we're going to have to calculate the center and radius of that, which is going to be a big part of the algorithm. And then we'll just figure out which one of those triangles, which one of the triangles that currently exists in the set of triangles that we've generated meets that condition or doesn't. If it doesn't meet the condition for that given point at that given frame, then we delete all those triangles, and then we collapse them all, and we're just going to use a mesh extrude node to do that, and then take the extruded points and then just collapse them all to the position of the target point at that frame in the simulation. So let's pop in a simulation zone, and let's just remove this join geometry for now. Just deal with our triangle. And then we're going to want first to get the index of the point that we're interested in. So the way that we'll do that is we will first add in a math node. Well, actually, maybe we don't need to do this. We can just do it by frame. So let's add in a frame, not that type of frame, a scene time node, which has the frame. And then we'll also want this to be confined to the number of points that actually exist. So we're just going to wrap that every time the index gets over the total number of indices in the points. So we'll use a domain size node to get the point count. And the domain size is going to be controlled by the points, which is in this geometry. So there's our point count. Then we can just add a math node with a floored modulo. So that just means that when this frame gets over the point count or equals the point count, it'll go back to 0 and it'll just loop through that. And so yeah, the frame floored modulo by the point count. And then we will sample index of this geometry at this index, and we're going to be getting the position because that's the attribute that we need to check against, because we'll check to see if the position of this point is for each of the faces, for each of the triangles in this mesh. If it contains this point, then we need to delete it and collapse them, and then move on to the next point and repeat that process. The core of this process is going to involve getting the circumcircle of each of the triangle faces within this mesh right here. So we're going to make a node group for this, and it'll just output the position and radius of the circumcircle as a field attribute for faces for each point. So let's start by just isolating one of the faces. I mean, this only has one face right now, so we might as well just use this input as our test. And the algorithm for this is mathy, and you can read about it and figure it out, or you can just convert algorithms that are available online. I would say I sort of understand this, but not in a super deep way, and I don't think it really matters. So this is the website that I got the algorithm from, and really I'm just looking at this and maybe some of the code examples that they have and converting those codes to nodes. I'm getting a little bit ahead of myself though, because what I just showed is just an algorithm for two-dimensional line-line intersection, which is a necessary part of finding the circumcenter of the circumcircle for the given triangle. But the overall algorithm, what we're going to do is we're going to find, we're going to take two of the edges of the triangle, then we're going to find the vectors that are perpendicular to those, and those are just like two lines, and then where they intersect, that's the circumcenter. And so for this triangle it'll be like pretty much right in the center. But if you had a triangle that was more squished, I don't know, like this or something like that, then take these two, and then their intersection is going to be out here, and it'll be the same for this. So you could take any two edges and where they intersect, or like the perpendicular vector to the edge vector, the intersection between two of any of those are going to intersect at the same point, and that's the circumcenter. So let me just delete this annotation. And the first thing that we're going to want to do is find those vectors. So we're trying to find the circumcenter and then the circumradius, which is just the distance between the circumcenter and any of the points of the triangle for each face. So this is going to be a attribute field that is evaluated on faces. And so what we need to be able to do to get these vectors is get the edges of the face based off of the index attribute of the face. And so what we'll do, let's bring this up here. So we'll take that index, and then we're going to go into our mesh topology nodes, and we're going to get corners of face. Then we're also going to do edges of corner, and we're just going to use this sort index. So the corners of a face are just like this other data structure. I'm not going to describe it completely correctly, but it's kind of like on one side, I don't know, there's probably some details, I'm not going to try, but I know that if I get the face index, there's going to be an edge that corresponds to that corner, and I just have to do two of those. So I'll just have a sort index 0 here, and then sort index of 1 here, and so then I just need two of these edges. I don't need all three of the edges, so I'm just going to do the first two. And so now I can just use the next edge index as my edge index. And okay, another cat situation. Buzz is biting my hands. 1 second. So now we will sample index. Well, actually, do I even need to do that? Can I do evaluated index? I probably can. Yeah, because it's the same geometry. So I'll keep on using Arendale's advice. Thank you, Arendale. So we're going to evaluate vector because we want the position, or we're going to want vectors at the next edge index. And we're going to want two things for our line-line intersection. We're going to want just the straight up position for both of these. Then we're also going to want the bisector, or the perpendicular vector that goes from the center of the edge in a perpendicular direction. And the way that we're going to do that is we're just going to get the edge vertices node, so we can get the positions of the vertices that make up the edge. And then we are going to get a vector from one to the other using vector subtract. So 0.1 minus 0.2. We're going to normalize it just for good form, so that makes the length of the vector 0, or sorry, length of the vector 1. And then we'll use a rotate vector node to just rotate 90 degrees about the z-axis. And then we can have two more of these. Let's move these up here. And we'll just have this rotated vector be the input. And so now we've got our positions and we've got our vectors. And now we are implementing that line-line intersection that you saw in the web page before. And so this is just converting math to nodes, or code to nodes. And so I'm just going to do it. So first we need separate XYZ. So we're going to need 4 of these. And what this is going to be is this is going to be the position of the start of one of the edges, and this is going to be the position of the end of one of the edges, and this is going to be the start and end positions of the other edge, or sorry, the other bisector of each edge. Trying to think if I even need this. I think I do. And so what that's going to be is, yeah, so it's going to be the position of each edge is going to be the first point of each of these. So that position goes there, this position goes there. And then we have this vector which needs to get added to this one to get the second point for each of the corresponding bisectors. Just add these together. Yes. And so now we have all of the information we need to implement that algorithm, which I'm now going to do, and we'll discuss that a bit in the time lapse. Here is the equation that we're solving to get the intersection between the two lines. And there's a little bit more in the article if you go to the link that I referenced before. That'll be in the description as well. But these are really the two equations that we need to get the x and y component of our output vector, which is going to be the circumcenter of our circumcircle. So what I'm doing in this time lapse is I'm just setting up the numerator and denominator of this division. So it's a bunch of taking x4, x3, so the separate xyz starts from 1 and goes to 4, and so the x component of the first separate xyz node is x1, and then the rest, so that's x1, y1, and then z1, but we're not using z at all. And then same for the next separate xyz is 2, so it's x2 and y2, and then the next one x3, y3, and then the next one x4 and y4. And so we're just copying this equation into nodes. So it's just subtracting things, multiplying things, and dividing things, and then we end up with this equation. And then to actually get the x and y components, we need to take the output of that first equation, which is ua here, and then do x1 plus ua times x2 minus x1. And so that's what we've got here set up in nodes, and that gives us our circumcenter. And then all we have to do to get our circumradius is use a vector math node set to distance and get the distance from the circumcenter to one of the points of the face. And so we can actually just use one of the face corner indices and just evaluate at index, set to face corner, set to vector, and getting the position attribute. And then we have our circumradius and our circumcenter, and we're good to go. But before moving on, we're going to check our work, because something that I find when implementing this sort of like math expression in nodes is that very easily you can make mistakes. So I actually paused the recording and checked it, and I found some mistakes, and I'm going to show them to you right now. First mistake is this is not x1 minus x3. This, so x1 is up here, x3 is right here, but this is x4. So x1 is correct. That's supposed to be x3. x1 minus, subtract x3, but it's minus x4. So minus x3, we'll correct that. And then also, second mistake I made is I forgot to set these evaluate at index nodes to edge. And they're all set to point, which is wrong because I'm getting the edge index. So I want to evaluate it on the edge domain, not the point domain. And then the last issue is that this divide, this is a very hard one to find because I accidentally just clicked clamp. That's set to clamp, and we don't want it to be clamped. And what you can do to test this, if you want, is, well, first let's put this all into a node group because this is way too big of a graph to just exist out here. So I'll press Ctrl G to add a node group. We don't need any inputs. We do need the circumradius and the circumcenter as an output to this node group. So we're going to group. This is going to be circumradius. This will be circumcenter. And then we're going to test this by, let's do circle. We're going to test this by creating sort of like a test triangle geometry. So we'll just, I guess, add a plane, delete one of the vertices, and we're just creating this so we can easily drag this around. Then we'll go in here, we'll add in a viewer node. We'll bring in that test triangle with an object info node, plane, which, we'll rename that to test triangle. Go back to your cube. And so now we can see that as our geometry. Let's actually pin this. So I want this viewer always to be on, so I'm going to pin this view and then duplicate it. And I'm doing that so that this pinning pins this viewer even if I go in here. Because if I just had one of these and I went here, you'd lose that view. So do that, do that. And then I want to add a circle, so curved circle in, that will then inherit the circumcircle of this single face in this geometry. And so let's sample index, and we're just going to sample index 0, so the face at index 0, there's only one face, so that'll work, and we'll get the position of that. Actually, no, we'll just get the circumcenter and the circumradius. So we'll do two sample index nodes. This will be a float, this will be a vector. The input to that will be the circumcenter, the input to this will be the circumradius. The radius will end up being the radius of the curved circle. I'm going to set this to 128 so it's a really good circle. Let's do a join geometry node so we can see everything together. So you can see how the radius is good, but we haven't applied the circumcenter yet. We'll do that with the set position node. And then the circumcenter will be the offset. No, this circumcenter will be the offset because we're evaluating it on that face. And so now you can see how the circle touches all 3 points of the triangle. If I go to this test triangle and I start moving around all these things, you can see how it is correctly creating the circumcircle. And that's a good way to test this, because if something was going wrong, it wouldn't look like this. So for instance, if I go in and I undo some of those issues, like if I check clamp, all of a sudden this point is way off over here and it doesn't make sense. Like in some cases it makes sense. I think if everything is within a certain range, you'll get the correct result, but other times not. So make sure that that's not set that way. And then the other issues of this is x4 instead of x3, again you have an issue. And then the same would be if we change these all to point, but you get the idea. I hope this is illustrative of a way of testing small parts of your network to make sure that the whole thing fits together well. It's a useful way to do some debugging. And in the spirit of debugging, let's set up another test to make sure that whatever we pop between the simulation zone start and end is working correctly. The way that we're going to do that is we're going to simplify everything so that we're just dealing with a single point, and we're also going to create just a static piece of geometry, in this case a triangulated grid, which will help us see if anything is wrong. We can get rid of that pinning view, and so we need two things. First, we need a point. Let's add an empty, and let's set the size just to 0.1, and we can hide this test triangle for now. And so this is going to be our point, which we'll get by using an object info node set to empty. So this location will be the point that we're checking the triangle's circumcircles against. And then we'll add in a grid geometry and we'll triangulate that. And let's set the vertices to 6. We'll need a new viewer node for this. So plug that mesh in there, and you'll see that this is our geometry. This is the point we're testing against. We're going to need the circumcircle node so that we can calculate the circumcircles for all of the triangles in this triangulated grid to test against this point location. And let's set this viewer to face, and then we can get vector math. So we want to get to test whether or not this point is within the circumcircle. We're going to get the distance between the point and the circumcenter of the circumcircle, and then if that distance is less than the circumradius, then the point is inside the circumcircle, and we need to delete that triangle. So the distance from the location of the point to the circumcenter, whoops, and then compare that. We'll set that to less than with the circumradius, and then we can see that this is working correctly. It's correctly showing which faces or which triangles need to be deleted. So let's go ahead and delete those faces. So we can delete geometry. We're going to want to delete a face. We're going to want to delete only the faces. And we're only going to want to delete those faces. So now you can see that those triangle faces are gone. But we still have an issue because this edge is still there. So maybe not only faces, maybe edges and faces. That looks better. But when you get to the border, these edges are gone, and you want those edges to exist. So we want these edges to be here. We want this edge to be gone. So how are we going to do that? We are going to do it by first evaluating this Boolean on the face domain. And then before we do any deletions or anything like that, we're going to capture that attribute so it stays the same despite geometry changes, and we're going to capture it on the edge domain. So evaluate on the face, but then capture on edge. And then we are going to delete only the faces on the face domain. And then we're going to delete again. This time we're going to delete edges, and we can't just directly plug this in there because you'll delete, oh, that's set to only faces. Set this to only edges and faces, but this will delete these edges as well. So we need to set up some conditions, and our conditions will be based off of the face count. So I can just pull in a face count, an edge neighbors node, which has the face count. And I'm also going to plug this into the edge capture attribute node. And then we'll add two compare nodes. So one, they'll both be integers, and this will be greater than. And so then we'll delete the edges if the face count captured before we do the deletion of the faces is greater than 1. And then we also want to say that we'll delete it if after the deletion of the faces, the face count, so not the captured attribute version of it, but the newly evaluated after the deletion of the faces, equals 0. And so what that would be is this one in the center will get deleted, because after we delete everything, it has 0 faces that are connected to it. And before it had 2, where these only had 1. So it fulfills both of these conditions. So oops, we need a Boolean math node, a couple of those. So we're going to want the original Boolean and this one and this one. And then we're going to delete these if all that is true. And now it is only deleting the faces and the internal edges that don't have any faces connected to them after all of the applicable triangles are deleted. And that puts us in a good position then to do our extrusion and collapsing. So we'll add an extrude mesh, set that to edges, and this selection can be this captured attribute because the only ones that exist from that set are specified by that Boolean. So you can see how even at the edges you're just extruding all those edges, and we can set that offset to 0, because what we'll do is we'll set the position. And we just want all of these we want all these points just to go to the position of the point in question that we're checking against. So those are specified by that top Boolean of the extrude node, and we'll set the position just to be the location of our empty. And there we get the collapse. So now I'm going to remove that viewer. You can see as we move around the geometry collapsing around it. This is the behavior that we want, and we have validated this process, and so we can then add it to our simulation loop because we feel confident in our calculations. So we'll make a little bit more space up here in our simulation zone. We can delete this viewer and we can hide this empty. Let's click back onto our cube, and we'll bring this up here. And instead of using this position, we use this position. And then instead of using this geometry, we'll be using the simulation geometry, input and output. And I believe we should be good to go. But we're not. It's not working. And it's not working because of a very small setting. This is wrong. So this geometry up here is points geometry, point cloud geometry. It's not a mesh. So this count is incorrect. But all we have to do is set this to point cloud, and then our simulation will run. Although it looks wrong. It looks like way too much geometry is getting added, which is, I believe, because I don't think we put in a merge distance node. So in this collapsing code, after we set the position, there's still 3 vertices in this mesh right here. They're all in the same position, but we actually need to have them collapse. So let's merge by distance, and let's just do this top and set it to something really high, just to make sure. And that is now looking correct. So we can watch slowly as everything converges to the solution. But if we don't want it to happen so slowly, we can add in a repeat zone in the center of this simulation loop. So let's move this over so we can get everything. Let's move this. Let's move everything over. Just get a little bit of space, and then add in a repeat zone. So again, we're going to want to just replace the inputs and outputs. So this will go in here. This will go in here. Wait, what's happening? Yeah, that goes there. Nope. That goes there. Then this goes here, and that goes there. And there's an issue with the repeat zone though, because we're using the frame to drive our target point index, and that won't really work here because I mean we'll just be testing multiple times, like however many iterations we have here. Let's set it to like 8. We'll be testing 8 times for the same point, which will produce odd results. And so what we want to do is increment it for each of these. And the way that we're going to do that is, instead of using this scene time, we're actually going to do a math add node. Math node, set to add. We're going to add 1, and so this is just going to be our index. We can change this to an integer, and this will just add 1 for each repeat zone iteration. Just move that right to the end, just add 1, put that there, and then also this will have to get carried over in the simulation. So now iterations are set to 1, so this should be the same as before, and it's not. And that's because we forgot to plug it in to this floored modulo. So plug that in there, and everything is working as expected. And if we set these iterations really high to like 80, the frame rate goes down, but overall everything goes faster. Let's set it to something like 32. There. So now the frame rate is fine, and you see everything converging. And we have in fact successfully implemented Delaunay triangulation. And you just want to set your frames high enough so it doesn't loop before it converges on the final solution of this triangulation algorithm. Oh, what is wrong? You know what I think is wrong? I think we need another merge by distance node, or we just need to take the selection out of that and set this to 0.001. I just want to see if this works. I'm pretty sure it will. I think that there's something where, yeah, I don't know. I'm just hoping that this works, because if it's not, then I have to go back and redo part of this tutorial because I will have made yet another mistake. You're seeing how the sausage is made. Nope, that's right. Thank the universe. So that concludes the meat of the simulation, but we still have some things to do. First, we need to delete all this geometry which is not inside the original mesh that we created. And then also you can see that there's something weird looking on this mesh, and that's the normals. So we're going to fix all that now. The way that we're going to fix the normals is we'll use a flip faces node, and we just want all the normals to point up 0, 0, 1. And so basically these are either normals that are 0, 0, 1 or 0, 0, negative 1. So what we'll do is we'll just flip them if the z component of the normal is less than 0. So flip those, and that looks nice now. For deleting this, what we'll do is we will get we'll just raycast from this geometry onto the original mesh, and if it's a hit, then it stays, and if it's not a hit, then it gets deleted. So add in a delete geometry node. We'll set that to face, keep that at all, and then we'll need a raycast, And then if it's not a hit, we'll delete it. So add in that Boolean math node to not. So the target should be our original mesh, which is here. So I can just add in another reroute, and I'll just bring that way over. Let me just make sure that this, I mean, I know it is, but yeah, that's the one. Okay, so we'll just take this and we'll say, wow, we want this all, well, let's do that there. Let's Control D, connect these. There's probably a better control for this, but I don't know what it is. And then set that to target geometry. And then the source position of the raycast is going to be just the position, but a little bit up the z-axis. So we'll just add 0.1. Ray direction is 0, 0, -1. Ray length 100 is fine. And so then you can see that it deletes all the geometry that we don't need anymore. And, you know, I think that just about covers it. This is a technique that actually just made this whole tutorial and this animation that preceded it as sort of like a side quest to a bigger, I was going to do some like inflated text using the cloth simulation code from previous tutorials, and I wanted to take text geometry, so not this curve, and then unwrap it and remesh it in this way, so I have this really nice triangulated mesh, and then use that as the basis of this like inflated text simulation. So that may or may not come to fruition. We shall see. But I'd never implemented this before. It's super fun to implement. It's super fun to use. It's a classic algorithm in computer graphics, so well worth learning if you're into that kind of thing. And I hope you enjoyed this tutorial. I hope you learned something, and above all, I hope you had fun. Until next time, bye.